Good afternoon and welcome to this session, lecture number 25 and 26 that I am going to cover in this 1 hour. So, this talk is about a DC-DC converter, dual active bridge, a special kind of DC-DC converter. So, why it is essential a DC-DC converter, that first I will discuss from the electric vehicle charging point of view, because nowadays the necessity for the DC-DC converter that has come because of this, majorly because of this. Okay. And another area is microgrid. Okay. Now, DC-DC converter, what happens? A DC-DC converter, what it does is it converts DC into DC. So, a DC of one level it converts into another level. So, since it is DC, it is just the conversion of voltage level. So, one DC, another DC. Now, the thing is, this could be of two type. One is having isolation, another one is not having any isolation, without any isolation. So, one is without isolation and this is with isolation. Okay. Now, the thing is, there are cases where you need isolation, where isolation is essential. So, in that case we use DC-DC converter with isolation. So, this is the symbol of DC-DC converter with isolation. Now, what happens in case of electric vehicle or in case of microgrid, there are several components that you have to connect to the microgrid. Let us say there is a microgrid, this is the microgrid DC bus, and then you have various components like PV, battery energy storage system, or maybe supercapacitor, or maybe fuel cell. Okay. So, let us say supercapacitor, fuel cell, then battery energy storage system, then PV. So, these many kinds are there. Thing that has to be noted here is, this is plus minus, this is DC bus, and then the type of the type of sources, the type of sources that we have here is, all of them are output is DC. From all of them output is DC. Now, the output type is DC, as well as the voltage level of different. So, voltage levels of BESS, supercapacitor, fuel cell, PV, everything is different. So, here the idea could be like, we might think that why not to make them equal, in the sense, why to use a DC-DC converter. Let us say we adjust the PV, number of PVs to be connected in series and number of battery to be connected in series. We manage in such a way that their voltage levels are equal. That can be done, right? The problem is that is fine. The problem is, yesterday in my talk that I discussed that if it is a PV, you have to extract power at MPP. Who is going to do that? If you are connecting PV, this PV you are directly connected to this DC bus. So, what will happen to this DC bus? What will happen? There is no control over PV power. So, it is working on its own. So, you need something, some power modulator or power converter or power processing unit, so that it can extract this power, PV power, at MPP, maximum power point, so that it can track. Because as we recently did experiments on PV, so we experienced that as very drastically I should not say, but because of weather condition, we have I will show you the figures. We have put the solar panels on the solar outside, and sunlight is coming, but it is sometime the sunlight is less, sometime it is more. So, power is varying like anything. Okay. So, in order to track the maximum power, you must have something in between. So, you need a DC-DC converter here. Okay. Similarly, BESS, what it does is, the major task of a battery energy storage system is to, if it is a DC microgrid, sometime what we do is we use it for maintaining this DC bus voltage. If it is a standalone microgrid, DC microgrid, we need a battery energy storage system in order to maintain the DC bus voltage. Now, question is, why PV cannot do it? Okay, why PV, why it is BESS or something else can be done, we will see. So, why it is BESS or battery kind of thing? Because in order to maintain bus voltage, any bus voltage, what you have to do is, so let us say there is a water tank. Okay. So, there is water coming and there is outlet also. Okay. So, let us say this rates are same R, then level of water will remain constant. Okay, rate, whatever rate water you are giving to the tank, you are taking at the same rate. So, what will happen, this the voltage level will be maintained, level of the water will be maintained. But let us say it happens that this has increased, this remains same, or this has increased, this has come down, this level will alter, either it will increase or decrease, right. So, in order to do that, you must need something else which is going to maintain, if you want to maintain, which is going to maintain this water level. How it can be done? Let us say you make a hole here, and from this hole you have a water reservoir, so that you can either take water from it or give water to it. So, it will act like a buffer, so that when there is a change in level and you want to maintain the level, there will be this buffer will come into act and it will maintain the water level. Similarly, here when, so everything is giving power. So, let us say fuel cell is connected, maybe wind is also there. So, PV, fuel cell, these are the two sources which are giving power to the DC bus. So, what will happen, if I have not shown load here, there will be load as well. So, when there is a load, what will do, so source is there. So, two entities are there, one is source, another one is load. If this is not matched, the power generated by source and power consumed by load is not matched, then definitely this DC bus voltage will not remain constant. So, in that case, in order to do the same thing, what you have to do is, you have to put something which can either store power or can release power. That is why it is either battery energy storage system or battery, that is the only thing that can maintain the DC bus voltage. Only thing in the sense, the electrical component which can either consume or release power, both can maintain the DC bus voltage. So, here also, in order to maintain this DC bus voltage, you need to control the power or control the current from the battery. Okay. So, that can be done using another DC-DC converter. Fuel cell I told yesterday, again I am telling today, that fuel cell, what it does, the characteristics of fuel cell is, voltage is very low, its current is very high. Okay. So, we have one fuel cell in our lab. So, that fuel cell is 1 kilowatt. Okay. If I remember correctly, it is 33 ampere is the output and around 40 or something around, so that it makes 1 kilowatt is the voltage level. So, voltage is less, current is quite high. Okay. So, here also the characteristics is different, you need another DC-DC converter, right. So, there are need for DC-DC converter, you can see in this microgrid itself. Similarly, when you have this, let us say the electric vehicle, there also there are parts where you need this DC-DC converters. So, what parts are those? So, let us see. So, the typical block diagram for electric vehicle is, you must be having a motor, then you have the motor controller. So, it is DC to AC. So, these are standard things. Then what you have is, you have battery, you have battery, then you have a DC-DC converter, so this is battery, okay. So, this is the motor electric vehicle motor, this is the motor controller, this is the DC bus. So, using this DC-DC converter, you are maintaining this DC bus voltage using this battery. So, one DC-DC converter you can see here. Another DC-DC converter, sometime what we are doing is people are trying to use ultra capacitor. I give this example to my students. There are supercars, okay, supercars that are now in the market, okay, that are available in the market. So, what they did is they instead of, so they have this IC engine is the main component for that car, but some portion in order to there is another motor which is electric motor which is going to assist the vehicle, okay. So, that is taking power from UC, ultra capacitor or super capacitor, they do not have battery, okay. That supercar, particular that supercar that do not have battery, it has ultra capacitor, okay. So, what it does is during acceleration it is taking energy from the ultra capacitor, and then when it is releasing then it can charge the ultra capacitor as well, okay. So, in that case also we have another DC-DC converter that is needed, and the work of this DC-DC converter is to maintain the SOC of the ultra capacitor, okay. You have to maintain the SOC of the. So, we can see one DC-DC converter, another DC-DC converter. There will be several more DC-DC converter will be there when it is a full fledged car. There will be converters for AC, there will be converter for lighting, there will be converter for several other components inside the car. Now, that is apart. Now, we can see there are two DC-DC converter, then another major DC-DC converter that we are going to talk about is how to charge this battery. So, how to charge this battery, what is the configuration, that I will come up, okay. So, here the things that I am going to discuss today is why electric vehicle, that is very common nowadays, okay. So, if I ask you the question that why we are using electric vehicle, what would be the answer? Anybody can, if anybody can tell me why we are using electric vehicle? What is the reason? Okay, pollution reduction, noise reduction, anything else? More reliable, okay, more reliable. And then what is the main reason why we are going towards electric vehicle? What is the main purpose?
Sir, gasoline fuel is getting diminished.
Cost will be less on this.
Cost will be less. I will come to that. And anything else?
Sir, petroleum resources are getting minimized day by day due to large scale consumption.
Okay, so the alternative to IC engine.
Yes,
okay. Anything else? Anything else? Majorly why we are moving towards the electric vehicle? Okay, this question generally I asked any short term course when I deliver a lecture, I generally ask this question and try to convince them what I am saying and try to convince them. But also today I will convey the same thing. Let us see whether you can accept this or not. Okay. So, the main purpose of the use of electric vehicle is to shift from the conventional fuel that we are using. We want to use green energy, that is solar or whatever renewable energy. Okay. Now, the thing is, if you are charging your electric vehicle from conventional grid, then the purpose of using of electric vehicle is not going to serve, because the grid, if I say for India, the power coming to the grid is majorly from coal based power plants. Okay. So, when it is not from renewable, you are charging your vehicle from renewable and you are charging from coal based power plant, then what is the purpose that you are using electric vehicle? You are making your city clean, but where this power plant is, it is getting more emissions, right. So, if you go and see car electric vehicle, if you see their specifications in the websites, it is available. They will not say its emission is 0, carbon emission they will not say 0, okay. Around I think 30 something, there the figure is 30, I forget the unit, the car's electric vehicle is I think this IC engine is around 100 plus, where electric vehicle is I think 30 or something. Recently I have seen, I forget that exact figures, 30, 33 it was. Electric vehicle has no emission, but still why we are saying 30 and 33? The reason is because if you are charging that electric vehicle from grid, then then that means the power plant is emitting something in order to charge the vehicle, right. So, if you are, so main purpose is put the renewables in place and then you charge your vehicle from that renewable, that is the purpose, that is why this electric vehicle should come into picture. Okay. So, that is why the reason. Then AC to DC converter, what we had previously and what we were moving towards, that we will see, and electric vehicle charging system, how this looks like, and then this thing I will discuss one by one. Okay. Now, this I already discussed. Okay. Now, let us move to this. Okay. This I think this is one of the most primary power electronic converter that we study, I think from 12th standard. Okay. A diode bridge rectifier in order to convert AC into DC, right. And also, so here what are the components that we have here is, so this is the input side and this is the output side. Okay. So, this is basically an AC to DC converter. Okay. So, I told you yesterday that we are engineers, we want something, whatever resources that is available to us, we will use it and let it work, that is the main purpose. So, that time the older days, maybe 30 years back, the purpose was to somehow convert AC into DC and use it. We wanted 5 volt DC. If you remember, I can show you this kind of adapters we had seen, many of you have seen, right, the heavy adapters for 5 volt. I think I have in my home, there is a home theater which is having this kind of adapter, which converts into, I do not remember, I think 9 volt DC, converts AC into 9 volt DC, where we have this bulky transformer, that we will see. So, the components that you have in this converter is AC to DC converter, source side. Then we have the transformer to match it, because if you want this to be 5 volt or 9 volt DC, from this is 230 volt AC, at home you have 230 volt AC. So, 230 volt AC means the peak voltage that you are going to get is around 315 or something, but you need 9 volts. So, there should be a step down transformer that you must have. Okay. And this step down transformer is 50 hertz transformer, this is not high frequency transformer. So, it is heavier, okay, bulky. Then you have the diode bridge or 2 diodes or whatever it is. When it comes to a product, they always try to optimize the number of components. And then you have a filter component that I have shown you yesterday, that you must need a filter at the output or input. Definitely you must have a filter here as well, but since it is power level is very low, so we are ignoring this transformer leakage impedance is sufficient enough to filter it out. Then at the output we are going to get DC. This was the configuration. Okay. So, it is a rectifier and power flow direction unidirectional, power you cannot feed from this side to this side, since it is diode. When there is a diode in your rectification process, you cannot do back power flow, means you cannot feed back power. Okay. Now, see, so this is the configuration. Okay, this is the configuration. If you do not have capacitor, these are known fact. If you do not have capacitor, then output voltage is like this. If you have capacitor, then capacitor will do the filtering. Even if how big is the capacitor, this filtering action will take place definitely. Okay, this will be there, definitely it will be there. Okay. Let us see what are the issues that we are going to have with this. Okay. Acha. One issue that we issues that we have here is power flow direction is unidirectional. This is one issue. Second issue is this one. Third issue is this one, this ripple, third issue. What is the fourth issue? Fourth issue is, you can see here, the source current that you are drawing is not sinusoidal, it is non-linear current, it is having lots of harmonics. This is fourth issue. Okay. Now, you might ask that why it was not necessary that time, why it is necessary to improve this source current quality, because the purpose I was saying that is that time it is 5 volt 9 volt charger, power level was very very low compared to power level that we are going to use for electric vehicle charging, where battery is taking substantial amount of current. So the source current that you are going to draw, if you use this kind of configuration, if you are going to charge your electric vehicle battery, substantial amount of current it is going to draw, and that will not be accepted by the grid. Grid is saying you maintain your quality. Utility company is saying they sometimes they impose fine also if your harmonic content and if your power factor is not proper, right. So these are the issues that you have. So this is what an experimental setup. So here you can see here, this is the diode bridge, full bridge diode bridge module, then you have the AC source, and then you have the this filter capacitor, and this is the load, and this is the output that we are going to have. Okay, let us see how it looks like. So this is the output, this is the DC voltage, output voltage, this is the AC voltage, this is the source current, and this is also this load current, this is load current. Okay. Now see, there is a major thing that you need to observe. I will come to that. Before that, you just see here, there is a ripple in the DC link, and I am saying that if whatever large capacitor you are going to use, this ripple will be there definitely. It will reduce definitely, but it will be there. This is one thing. This is 50 hertz, 100 hertz ripple. This is 100 hertz ripple, low frequency ripple. Okay. Second thing is, as AC source voltage is changing, this voltage will change. You cannot maintain this voltage. There is no closed loop operation, since it is an uncontrolled rectifier. So this voltage will change, and you can see here the source current looks like this. Now because of the source current, you see what major impact that you are going to have on the grid voltage. This is the thing that you must see. Now see, I have drawn here source voltage like this, but you see what source voltage, the source voltage we are having at the plug point at the lab supply. What is the voltage? So what is the significant thing that you need to see? You see, we have flat topped voltage, flat topped AC voltage that we are getting. Why this flat top voltage we are getting? Anyone can explain why we are getting this kind of voltage? AC voltage. Instead of sine wave, we are getting a flat topped voltage. What could be the reason? Okay. Reason is this current. Reason is current of this type. We have multiple PCs, okay, PCs, and the SMPS that we have, that is taking current like this. It is having diode rectifier at the input. It is taking current like this. Now this is the AC source, and then this is the inductor. So this voltage may be sinusoidal, but there are some line inductances are present, and this is the voltage that we are measuring here. Now since this current is like this and it is available at the peak of the sine wave, so what happens? During this period only there is a drop in the inductor. Rest of the period, this period, there is no drop. That is why it is not affected much. But during peak period, the current exists and there is a drop, and that is why the voltage is appearing like this. So if you have current like this, then it is going to affect the grid voltage, the voltage at your premise as well. So all, if I summarize, then this is not the state of art for electric vehicle charging system. We cannot accept this. So what could be the, so this is what I was talking about. So what are the issues? So we want to eliminate this low frequency bulky transformer. Power factor improvement should be there. Power quality improvement, both input and output. So bidirectional power flow, this is necessary. Why? Because nowadays we are looking for vehicle to grid, grid to vehicle, as well as vehicle to grid power, or vehicle to grid, or vehicle to building. People they say vehicle to building now, vehicle to grid also possibility is there. Now power factor, power quality improvement both at input and output means this output voltage will be steep voltage. Okay, voltage will be maintained, regulated voltage, and then input the current quality that we are going to improve. Okay, so these are the configurations electric vehicle charging system currently that we have. So AC supply is there, then you convert it into DC, and then you use another DC converter, and then your electric vehicle is there. Okay. So this could be non-isolated or isolated. Okay, isolated, and unidirectional and bidirectional both you can have. So non-isolated unidirectional, non-isolated bidirectional. Okay, bidirectional. So bidirectional. So here, so this is non-isolated unidirectional, this is non-isolated bidirectional, this is non-isolated unidirectional, this is isolated and bidirectional. Okay. So this is where the DAV converter exists. Here we have the DAV converter. Okay. Now let us see what are the possible converter configuration first here, then we will see to DAV. Okay. Now, so this I already explained. So we have two stages, one is the grid side converter and another one is the vehicle side converter, and bidirectional is necessary. In order to, necessary means it is, people say yesterday also I was talking about product level thing. Product level thing means some idea like it is if it is necessary, then only you go for it. If it is vehicle to grid is necessary, then only you give the provision for it, because when it goes to vehicle to grid, it has to be bidirectional. Things become complex, more complex. Things become the system becomes more complex, and the control also becomes complex, because you have to adopt with so many sensing and control thing. Okay. So this is one of the very famous bidirectional converter. This is a PWM rectifier. Okay. So using this, so previously we had only what, a diode bridge rectifier. So there here also we definitely we need a DC converter, a transformer. We need a transformer here, definitely we need a transformer. Okay. But the thing is, with this what we can have is, what we can achieve is, this voltage will be regulated, this output voltage. So regulated output voltage, and at the same time this current what we are going to get is, this can be at unity power factor and sinusoidal in nature. So just diodes we have replaced with this. Okay, these are MOSFETs. Okay, so with fully controlled devices, what we can have is two things we are improving. One is regulated DC output voltage, and the power quality at the input side is significantly improved. Okay, at the expense of what? The semiconductor devices. These are costly devices. Then it comes with sensing arrangement, then it comes with driver circuit, necessary power supply. That was simple, easy, but limited capability. Here you have more advanced thing, but with control thing. Now here we are sensing the current, and then with the reference current. So sensing sinusoidal current, and then okay. So how DC link voltage is maintained? So we are sensing the DC link voltage, then it is compared with the reference DC voltage, and then it fed to the PI controller. Error is fed to the PI controller, that is generating some DC value here, which is multiplied with a sinusoidal template in order to generate a sinusoidal reference current, and that is compared with actual current, and then PI controller is generating the voltage, converter voltage, and that through PWM controller you are generating the PWM signal for the switches. This is the simple control, that is now universal. Okay. Now we have two control loop, one is DC link voltage control and another one is, so DC link voltage control is here, another one is this current. So you can see here, this is the source voltage and this is the source current that we are going to achieve here with the PWM rectifier. What we had previously with pulse current, now it is a purely sinusoidal current, not pure sinusoidal current, I must say. It is a sinusoidal current with high frequency ripple on it, which is easy to eliminate. Previously it was the low frequency harmonics like third harmonic, fifth harmonic, seventh harmonic exist in source current. Now it is high frequency which can be easily eliminated, and this is the DC link voltage that is maintained at a constant value with ripple. When it is from single phase, this ripple you cannot avoid, okay, and this is the harmonic profile. Now there are several such topologies, okay. So this is the PWM rectifier, then we have I will come to that. So bridgeless interleave PFC. Now this topology, just you look into this topology. So what we have is here this very famous topology, and you must be familiar with it. So what we have is source voltage, source AC voltage we have, and then using a diode bridge rectifier we generating an AC, we generating DC, and then we have this is called DC boost converter. You can see here boost converter, okay. So using this, so this is AC stage, AC to DC stage, and then you have boost converter means it is DC to DC stage, okay. So two stage, but the problem is, as I told you, since you have a diode bridge rectifier, so this is not bidirectional. If this is not bidirectional, this DC-DC converter that we are going to use is unidirectional. So here also the bidirectional power flow is not possible, but the thing that we are going to get here is, one is this current will be improved, this current quality will be improved, and then this voltage you can maintain, this output DC voltage can be maintained, but you cannot eliminate this high frequency transformer, because you have to match the voltage. You cannot and bidirectional power flow is not feasible. Here bidirectional power flow is feasible, DC link voltage is maintained, this current is maintained, but transformer you cannot eliminate. Here also same, here it is interleaved. So you can see here we have two boost converters which are interleaved. So one boost converter is this one, and another boost converter comprising these three. So this interleaving we do in order to increase the main purpose. Yesterday I was telling, multi-level converter is main purpose is to improve the to make the converter capable for high voltage application. Here also interleaving is done. First thing, the purpose is to increase the current capability of the converter. The advantage that you are going to get is the reduction in current ripple and other advantages that you are going to have, okay. But here also you have the same thing, you have the AC to DC, two stages, and then you have DC to DC. So transformer is still there, and then bidirectional power flow is not possible. Just I had two slides to show the comparison. So you can see here the currents, this is the source voltage, and these are the currents from all those four converters that I have shown, and then this is the ripple in the current, okay. So only thing is they are having almost same feature. Only thing is in PWM boost input current is the frequency is little bit, means twice, frequency is half compared to these three cases, but does not matter because it is at 25 kilohertz, it is very high frequency. So input inductor is sufficient enough to filter out this thing. These are the loss comparison, okay. So yesterday I was telling you that since it is multi-level converter, the switching losses are less. These are what? These are not multi-level converter. These are conventional two-level converter. That is why you can see here IGBT switching loss or MOSFET switching loss. If you can see, significant component which is higher compared to conduction losses. Okay, this is what I mean to. So this if you see, this has been done. The switching frequency we have taken 25 kilohertz, which is for multi-level converter, this is less than 2 kilohertz. So there the switching losses are not that significant, but here switching losses are significant. That is why most preferred switch could be MOSFET, okay. IGBT, not even IGBT, MOSFET is most preferred at this power level, okay. Now if we compare here, so you can see here, so compare V4 converters. So these converters are unidirectional, but PWM PFC which is bidirectional in nature, and then these are ripple and all we have compared, but the thing is, the main thing is, for all this the problem is this transformer, low frequency transformer you have to have in place, okay. So what next? So, the possibility is this is the DAB converter, DAB DC to DC converter. Now, there what we had, so let us say AC, so AC is converted into DC, then you have this DAB. Okay. Now, let us say this is some voltage level Vs, corresponding to this voltage level you are generating the voltage level at this DC bus. Then you use this DAB to step down this voltage, okay, to step down this voltage. So, what is the configuration of a DAB? So, you see here you have input DC voltage and output DC voltage. In between we have a high frequency transformer, this is the high frequency transformer. Okay. So, high frequency transformer, then we must be having one inductor, I will tell you what is that. But the thing is, when it is high frequency transformer, the core size reduced significantly. Significantly means I will show you, we have one 2 kVA 3 winding transformer, high frequency transformer, 20 kilohertz transformer. I have figure, I will show you at the end of this lecture. Their size, you can see how much small size it is, okay, and size reduces, also the weight of the transformer reduces, though. So, this is called high frequency link. So, you are linking these two sides through a high frequency link, and that is doing the stepping up or stepping down, whatever necessary, that is doing. So, you do not need low frequency transformer. So, one example I can give you, adapter I was talking about, like for speakers we had those heavy adapters. Nowadays what you have? You have this mobile chargers, you have this laptop chargers, there you will not find that is heavy, right. Mobile chargers are very lightweight, but mobile, what is the voltage level of mobile? Maybe I do not know, means is it 5 volt, around 5 volt. So, 230 volt you have at your home and you are making it 5 volt. How that stepping down is done? Definitely some kind of, if isolation is there, definitely high frequency isolation should be there in order to accommodate that transformer inside this small piece of box that you have as a mobile charger. So, this is high frequency link, gives you compact size, also this lightweight, and then, but previously we had very less number of switches. Here what we have is, we need to have 2 edge bridges at the input and output of the high frequency 2 winding transformer. So, this edge bridge and this edge bridge, the purpose of this edge bridges is to convert this DC into AC, square wave AC or quasi square wave AC, that we will see, and then also here also this DC into AC. So, this is the configuration of a DAB. So, we have 8 total active switches, then a high frequency transformer and 2 filter capacitors, and then there is a need for an inductor in order to control, in order to have a current control. So, what is the equivalent circuit? This is the equivalent circuit. Whatever voltage that you are generating, square wave voltage that you are generating here is reflected here, that is referred. There is a square wave, input side also you are generating square wave here. So, one square wave, another square wave, there is an inductor in between. So, it is simply just one voltage vector Vp, and then just by placing this V secondary, that is feasible, V secondary, the current through this inductor can be controlled. How it can be controlled? Okay. So, in DAB this is isolated bidirectional DC-DC converter. So, this is bidirectional in nature, this edge bridge, this is also bidirectional in nature. So, entire transformer is bidirectional in nature. So, now this kind of configuration has the capability to let the power flow either from this side to this side, or power flow from this side to this side. So, if you use this as the second stage of that EVCS charging system, electric vehicle charging system, then you are making your system capable enough for bidirectional, that is grid to vehicle and vehicle to grid mode of operations. Okay. So, this is the inductor drop, and this is the primary voltage and this is the secondary voltage, this is the phase shift. So, here the power flow control can be achieved this edge bridge okay. So, this edge bridge is generating a square wave, this let this as a reference okay. So, why we are employing a phasor here, because first harmonic analysis we can do on this okay. So, that phasor diagram correspond to first harmonic. So, one Vp, so Vp phasor diagram, so we have drawn as reference Vp as reference, and we have freedom to place this Vs phasor at any place, we have freedom, that freedom. So, let us say we are putting this at a lagging power factor, this you can control, you can by switching action you can impose this phase difference between the Vp and Vs dash. If you do that, then this is the inductor voltage drop and this is the inductor current. Now, you can see here, just do not change the length of this. If the length of this phasor and this phasor we are keeping constant, just mere changing this position of Vs prime, what we can see is either it could be here or it could be here, it is up to us, we can even merge them. If we merge them, there is no current, there is no drop in across the inductor, there is no current. As you increase this phase shift, the current to the battery starts increasing. So, like that you can control the current to the battery. So, what actually happening? What actually is happening? Now, what happens when you are, so this is constant. Now, voltage you are not doing anything, its phase you are not doing. So, this voltage, this square wave voltage is constant, you are not doing anything, this voltage is constant and you are keeping this constant. So, this you are not doing anything, you are controlling this voltage, you are controlling, that means Vs dash you are controlling. As you are controlling this Vs dash, the drop across this is changing, and accordingly this current is changing, and hence the current flowing to the battery, this I battery eventually is changing. Okay. This is, so when you want the current to flow from one side to other side, make that other side lagging. If you make other side leading, then current will flow from that side to the primary side. Okay. So, this bidirectional is feasible. Now, as I told you, now there is a square wave you can generate. Okay. This is now immediately the question may arise, because when I started studying DAB, that question has come to my mind, that why not to do PWM, why not to use PWM here, can anybody tell me? We are saying the square wave we are generating square waves, why PWM is why not PWM? Generally square wave was the state of art for the home inverters. If you remember, even in my native place we have an inverter which is square wave inverter. Nowadays it is sine wave inverters are more prominent, okay, means in performance point of view, and everybody is using sine PWM inverters. Now, again for this DAB converter we are using square wave, why not sine PWM? Any answer? From online participants also, why not sine PWM we are doing here? Controlling. Okay. See, what information that I missed here is, this transformer is of very high frequency transformer, which is 25 kilohertz. Operating frequency is 25 kilohertz. That means the square wave that we are generating here and here is of what frequency? Something around that frequency, 25 kilohertz range, right. Now, when we do sine PWM, if it is 50 hertz, we use 25 kilohertz. Now, our fundamental wave frequency is 25 kilohertz, then what would be our PWM frequency, PWM waveform frequency would be. So, here it is whatever times that you have to that you multiply, and then you have to have some some hundreds of means some very high switching frequency, that these switches are not capable enough, and also we do not allow this because switching losses will increase. Okay, switching loss will increase. Now, here one point I need to mention very important, that we try to go as high frequency as possible. We are trying to go towards that. What is the reason for that? We are trying to go very high frequency up to, I have seen a lab prototype which is designed for 100 kilohertz. Okay. So, we are going towards that. Why? GAN devices we are planning to use, SiC devices we are planning to use, we are using SiC devices we are using. Why we are doing that? Means why it is necessary to go for very high switching frequency? Any idea? One is size is component size is reducing, but still we try to go further because we want the size to be reduced further. Okay. But the problem is, as you are increasing frequency day by day, the switching losses are increasing significantly, switching losses. Okay. Devices are almost same, switching losses are increasing. So, if switching loss increases, the problem is, what is the problem if switching loss increase? What is the problem? Heat will increase, heat sink size will increase. You are trying to reduce the size of the product, because of the loss heat sink size is increasing. So, it is inversely proportional. So, what it does is, the one advantage of using this DAV converter is, you operate at very high frequency, it gives you the freedom to operate in ZVS condition, zero voltage switching condition, to reduce the switching frequency. That advantage that you are going to have, or that feature you are going to have with the DAV converter. If you go for more or less any standard paper that work with DAV converter, they talk about ZVS in order to reduce the switching losses significantly, that freedom that you are going to have. So, here what are the advantages that you are having? One is bidirectional power flow, voltage matching capability using a high frequency link, where you are having where you are reducing the size, and also this ZVS capability that you are going to have with this. Now, the modulation scheme that you are going to have here is a 4 modulation scheme. One is single phase shift modulation, extended phase shift modulation, dual phase shift modulation, and triple phase shift modulation. So, you see here, this is SPS, EPS, DPS. So, what are these? That let me explain. Okay. Now, see the primary and secondary square waves are presented here. Primary and secondary square wave that you are generating are presented here, and it is marked as alpha 1, alpha 2 and alpha 3. Now, you see here, when it is single phase shift control, only one phase shift we are giving, though we are having possibility to give 3 phase shifts, but we are giving only one phase shift. So, here alpha 1 and alpha 3 are making 0, and only phase shift is the external, alpha 2 is called what is external phase shift, I will tell you. So, when alpha 1 and alpha 3 is 0, so this becomes a complete square wave, which is this one, and this becomes a complete square wave, which is this one. Okay. And there is a phase shift between this 0 crossing and this 0 crossing. This is called, this is alpha 2, this is alpha 2. Okay. So, in single phase shift control, alpha 1 and alpha 3, these two are 0. So, you have 2 square waves, and then you have alpha 1 and alpha 3 equals to 0, and then alpha 2, there is a phase shift, you need a phase shift, otherwise no power flow will happen between primary bridge and secondary bridge. In EPS is a very famous modulation scheme for DAV converter. So, I will tell you what is the reason for it, but first try to understand what is EPS. In EPS, what they are saying is alpha 1 is 0. So, alpha 1 is 0 means this, alpha 1 not equals to 0. That means the primary bridge the square wave it is generating, which is a quasi square wave, whereas the secondary bridge that is generating a square wave. Okay. So, what is the advantage of using it as a quasi square wave and square wave, that I will tell you immediately, but before that you just see this is a quasi square wave, this is a square wave, and there is a phase shift, external phase shift. The phase shift which is between primary edge bridge and secondary edge bridge voltage, what is the difference, phase difference, that is called the external phase shift, which is not 0 for all the cases. You can see here alpha 2 is not 0 for any of the cases, because in order to transfer power from one side to other side, you need an external phase shift between two voltage phases that is available on primary side and the secondary side. Now, EPS, the primary side quasi square wave. So, similarly for DPS, dual phase shift, both are quasi square wave, the primary bridge voltage and secondary bridge both are quasi square wave. And in TPS, what happens in primary in DPS, these two are same, means this is same for primary and secondary bridges, these two are same. For TPS, these two are not same, for TPS these two are not same. Okay. Now, you see here with two edge bridges, we have these many degrees of freedom, 4 degrees of freedom that we are going to have in corresponding to control perspective. Here we will discuss about this modulation, only these two modulation scheme. If you understand these two modulation scheme, you can employ, means this can be extended to this also. Okay. What is the reason that we are using this quasi square wave? Okay. Now, see, the phasor diagram was something like this. This is inductor current phasor, this is VP primary bridge voltage, this is secondary bridge voltage, okay, and this is the inductor voltage drop, okay. This is SPS, single phase shift control, where the primary voltage and secondary voltages are defined by the transformer turns ratio and the two DC voltages on primary side, secondary side. There are many complexity to this, that I will tell you, just one complexity I will tell you. And so, the only thing that we introduce is this is the phi 2, alpha 2. Okay. This phase difference for SPS is alpha 2. Okay. So, this is only thing that we have here, only thing in SPS, nothing more than this. Now, what it does is in EPS, what it does is, now see, this is the primary bridge and this is the secondary bridge voltage for EPS, this is EPS. Okay. Now, since it is a quasi square wave, what we are doing actually, since it is a quasi square wave, previously it was like this. So, whatever primary fundamental peak you were getting was this one. Now, when you reduce the width of the pulse, because now you have on the primary side you have this so you introduce this alpha 1 that you have introduced, because of which now the fundamental peak is reducing. That means what? The length of this phasor is reducing. Now, in EPS, this is VP dash. So, that means what? With EPS, with alpha control, alpha 1 non-zero, you can reduce this voltage phasor. So, this freedom that you got, and because of that some advantages that we are going to get, that I will discuss in the result section. Similarly, in DPS, what happens? Now, you have control over both this phasor also, this phasor also. That means, by introducing this internal, these are internal phase shifts and these are called external phase shift. So, internal phase shift in case of SPS was 0, we do not have that freedom. For other modulation schemes, we have this internal phase shift option is there. So, our degree of freedom is more. So, by doing this, we can minimize the back power flow. Back power flow means what? In SPS, what happens? There is a power that is delivered by the source and the load is not capable enough to consume the entire power delivered by the source. So, the source is delivering some amount of power, let us say 100. So, this is supplying, let us say some amount of power, let us say 100 watt. This load is not capable enough, it is consuming only 90 watt. I am assuming there is no loss in the system. Then what happens? This 10 watt, this is going back, 10 watt is going back, though it is not utilized by the source, it is coming from the source, but not utilized, coming back. What will happen? The switches are more stress. The current supposed to be for 90 watt, now the current for 100 watt is has to be definitely more and switch ratings are more. But what happens in case of EPS, this backflow power can be minimized and even can be made 0 in order to reduce the switch stress. That is the main purpose of introduction of EPS. Okay, so, in SPS, so these are the square waves that we generate and this is the inductor current. So, here in so the square wave is generated at 50% duty ratio and there is no phase shift, there is phase shift between two bridges is controlled. So, only phase shift that we have, as I repeatedly told, that it is only the external phase shift that we have, internal, there is no internal phase shift. Okay. So, this I already explained. This is one of the most simplest form of modulation scheme for DAB converter. We have we finished one project. So, that project is on a TAB converter, triple active bridge converter. There we implemented using SPS. Okay, there it is not DAB. I will show you the result. I will show you the setup. And in EPS, what it does is, this is the primary voltage, primary bridge voltage, this is the secondary bridge voltage and this is the inductor current. Here you can see that this voltage is a quasi square wave voltage. Okay. So, here we have two duty ratios, alpha 1, alpha 2 and alpha 3. So, alpha 1 and alpha 3 are equal, only alpha 2 is different from the alpha 1 and alpha 3. So, this is outer phase shift, which is actually we have considered alpha 2 and the internal phase shift. So, here alpha 1 not equals to 0 and alpha 3 equals to 0. So, for this bridge there is no internal, this is internal phase shift, inner phase shift, which is not, this is outer phase shift. Okay. Now, at this point let me tell you one important thing that happens in case of DAB when you employ for battery charging. Actually, the paper which introduced extended phase shift, that is they have connected DAB between two microgrids, where the grid voltage, both the grid voltages are defined. When the grid voltages are defined, there is no issue. But when you employ this for battery charging, what happens? One side is fixed, let us say primary side. So, the paper which introduced DAB, the EPS, there the system they had is, this is microgrid, this is microgrid with defined voltage, which voltages are constant. But when you employ this for battery charging application, from a constant voltage, because previous to this what we have is power factor correction circuit. So, it will maintain the DC bus voltage. So, this voltage is constant, but what happens to this, as battery voltage, as you are charging the battery voltage is increasing. So, when battery voltage is increasing, what will happen? This phasor is not constant anymore. This phasor, what we are assuming, this phasor which is secondary voltage is not constant anymore, this is changing. Okay. If this is changing, then you have to adjust either this external phase shift, or if you are employing EPS, you have to employ extended EPS, or sometime it is needed that you employ DPS in order to deal with this issue. You understood the problem that we have. Here the voltage is not constant. Here the two bridge voltages are not constant, input voltages are not constant when it is a battery. Okay, these are standard things, that is how to calculate the duty ratio, which is available in that paper. Okay. Now, let us talk about the back power flow. Okay. Now, see this is SPS, this is SPS. Okay. Now, see here we have primary bridge voltage, we have secondary bridge voltage, and there is a phase shift, this is the phase shift. Okay. And this is the inductor voltage, because this difference will be definitely the inductor voltage, the difference of this voltage definitely will be the voltage across the inductor, and this is the inductor current. Now, you see here the input power drawn from the source is having some negative portion, that means what? The power is flowing back to the source, that means some power was already came, and that now you are feeding back that power, it is not utilized by the source load. Now, this is with EPS waveform. Okay. Now, you see here there is no negative portion, that means the back power flow can be adjusted to minimum or sometime can be eliminated as well. Okay. So, this is quasi square wave, this is square wave, and this is the voltage across the inductor, and this is the inductor current. Okay. So, this is inductor current and inductor voltage. Okay. So, with this I have come to the conclusion that so here what we have explained about, the EVCS, electric vehicle charging system, mostly single phase. If it is on board, you can think of on board also, and we have used the secondary stage, we can use secondary stage as a DAB converter, since the DAB converter, the size can be reduced, the losses can be reduced by ZVS operation, and its controllability is much superior. Okay. So, conventional diode bridge rectifier are not fit for this EVCS. PXC converters are needed at the front end in order to improve the input power quality. DC-DC converters are needed at the secondary stage, and DAB converter is isolated. When you have a battery, there is a need for isolation sometimes, and nowadays it is becoming a practice to have an isolation, and then because of bidirectional capability, we can achieve grid to vehicle, vehicle to grid operation. Okay. So, though SPS modulation is less complex, EPS modulation more degree of freedom to control back power flow and ZVS. So, these are the some prominent references, and thank you. So, I am open to take up questions from online, offline participants. So, if you have any query. Okay. Yes, yes. I wanted to show that that picture. Yes, thank you. I forgot completely. Not this one. Another one should be there. Okay. This one. You see here. So, this is the prototype that we have developed under that project. So, here you can see here, instead of DAB, so here we have 3 edge bridges, edge bridge 1. So, here this is the high frequency transformer, this is the high frequency 3 winding transformer. These are the 3 edge bridges, this is the inductor, and this is the DSP microcontroller, and this is the pen. I put that pen in order to let you know what is the size of this configuration. Okay. And this is the driver circuit, and this is what we have developed for field testing. And so, here you can see is the size of the transformer is small enough, and these are the battery and battery energy storage. Another figure, field testing figure here. So, we did it with solar panels also, since during that time this weather condition was not that suitable. What we did, instead of solar, we tested with the DC voltage and supplying from a diode bridge rectifier in order to get the validation of this topology. Now, here some of the, so here some of the results, if you can show the results, if you can show the so inductor current and edge bridge voltages you can see here, inductor current, edge bridge voltage, and here you can see the battery current. We have charged the battery, and these are the square wave voltages that we are generating at the output of the edge bridges. Okay. So, this is how the DAB can be helpful in electric vehicle charging or battery charging, or integrating DC microgrid and other in place of other DC converter we can use it, but you have to keep in mind whether this converter is really necessary for that particular application. In power electronics you can do many things, but my suggestion is always try to look whether that application is looking for that thing or not, then only employ that suitable converter. Okay. Thank you.